Hello and welcome back. In trigonometry today, people do not actually like arccoses, arctans and arcsines, particularly if they appear in equations or relationships. So today we're going to do a simple example. 2 times the arcsine of 2/3. We need to show that in fact it is equal to the arccos of 1/9. Okay, so we can just learn a few techniques and a few approaches into solving problems which look like that. This is not an equation or anything like that. It's just a fact. So you can actually put it into your calculator and verify that these two quantities are in fact the same. So how do we actually come to prove something like that? There's a variety of methods, so I'm going to show you a few today. Let's look at the method 1. So let's have a little think about what we could do for something like this. Method A. It's fairly common to think of the arcsine and the arccos and the arctan as angles. Quite strictly speaking, they're not angles, of course they're functions, but it doesn't harm to actually think of that as saying perhaps 2 theta, where theta is of course the arcsine of 2/3, is equal to an angle phi, where phi is equal to the arccos of 1/9. And because we're trying to, this is not an equation to solve, is basically a good idea to start with the left hand side. So take that as a given, 2 times the arcsine of 2/3, and see if we can come up with an expression in arccos. And this is how we can do that. So by writing this relationship here, I can actually say, you know what, 2 theta, so theta is the arcsine of 2/3, which is positive, of course, and therefore it's an angle between 0 and 90. I use the word angle, and therefore using this fact now, I can actually put it into a right angle triangle. So I can say, okay, if the arcsine is 2/3, this is my angle theta, that means that the sine is equivalently, that says the sine of theta is equal to 2/3. So looking at this particular triangle, opposite divided by the hypotenuse in the ratio of 2 to 3, quick Pythagoras will tell us that this is actually the square root of 5. So from this triangle now I have at very quickly the cos of theta, the tan of theta, and anything else I might need. Okay, so far we have there 2 theta is equal to phi, and we want to find out what is this phi. And because the phi is an arccos, it makes sense to actually cos both sides of this equation. We can actually say, okay, let's take cos this. So the cos of 2 theta will definitely be equal to the cos of phi. What can I do for this cos of 2 theta? Not a lot of things at the moment. I cannot use my triangle because remember, my triangle will give me the sine of theta is 2/3. It will also give me the cos of theta if I need it. Of course, it's going to be equal to root 5 over 3. It will also give me tans. The tan of theta from this triangle, of course, is going to be 2 over root 5. So I can actually get something to do with theta, but not cos of 2 theta. But I do have identities, normal identities, like the double angle. So I can change that into one of its equivalent expressions. I can go, of course, as 2 cos squared theta minus 1. That's definitely an identity. And that will be equal to cos phi. If I go for this particular version, of course, I know what my cos of theta is. From there is root 5 over 3, I'll square it and I will have my cos phi. But if we didn't know that, perhaps we can actually use, we didn't even need to actually get anything more from a triangle. We could actually use the sine, and we could have used here, I'm not going to do it now, I'm not rubbing off, 1 minus 2 sine squared theta. It's another expression which is also true for the cos of 2 theta. So I could have put that instead and use the value of 2/3. Since I already written it in cos, I can now say, looking at my information there, 2 lots of, I'm writing stupid things, I do apologize, I didn't substitute anything, 2 lots of the square root of 5 over 3, that's of course my cos of theta, or squared minus 1, will be equal to the cos of phi. Squaring that is going to give me 2 lots of 5/9 minus 1 is going to equal cos of phi. And then, of course, that's 10/9, take away 1. So 10/9 take away 9/9. 1/9 is equal to the cos of phi. And, of course, your phi, okay, is going to be equal to the arc cos of 1/9. Okay, so I think we are pretty much done, because, of course, if you look at what we said up there, we said that 2 theta, where theta is the arcsine of 2/3, is some angle phi, and it turns out that phi has to be the arc cos of 1/9, and therefore we can conclude that this is in fact true, and we're done. So that's method A. What else can we do actually to solve this problem? Is there another way? Me personally, when I first started doing that as a student, perhaps, this is kind of the techniques I was using, and they make sense, and I was very comfortable. But now, these days, I'm using a variant of that, which is a little bit half and half of what we just done up there. So again, I'm going to say, let's call this thing here an angle theta, and we're going to try to find some angle phi which has this property. So what can we do in there? If we call this theta, so theta is the arc sine of 2/3, and I do stress this is not much different as method B, it's just a variant, and equivalently the sine of theta is equal to 2/3. So I'm going to take this equation here. 2 theta is equal to phi, where theta is, of course, the arcsine of 2/3, and phi is to be found. Okay, I'm going to take cos on both sides. Cos of 2 theta is equal to the cos of phi. I don't need any triangles for this particular one, because, of course, I can use directly the information that I have been given in there. So I can say 1 minus 2 sine squared theta, that's an identity, is equal to the cos of phi. 1 minus 2 times, squaring now, the sine of theta is, of course, 2/3, all squared, equal to the cos of phi. That's 4/9, doubled is 8/9, is equal to the cos of phi. And we have cos phi is 1/9, and therefore phi, whatever this thing will be equal to, the required answer is the arc cos of 1/9, and we're done. Okay, so that was like a little variant. We didn't have to use any triangles for that, for this particular problem. Is there another way we can actually use for this particular problem? And the answer we can perhaps do, if we're having double angles usually, or not double angles, but when I mean like 2 times something on one side equal to an angle on the other side, we can actually use a geometric method. And I'm going to try to explain to you how this will work for something like this. Again, 2 theta here is equal to a phi to be determined, but the theta, of course, has this property. So what I can do there is I can draw my right angle triangle again, but I'm going to work very, very differently, because I'm a GCSE student and perhaps I don't know anything about double angle in cos. So there's my right angle triangle, and if the sine of theta, let's say theta is here, actually let's put theta here, it's actually easier to draw. Okay, if the sine of theta is 2/3, that means this is 2, 2, 3. And of course I can do Pythagoras and find this side, but that is not strictly speaking needed. I needed 2 theta now in my problem. 2 theta, where can I put this 2 theta in the picture? All I'm going to do is I'm going to put another triangle identical to the one I've just got there, okay, but on the other side. So the sharing obviously a height, and this is 3 on this side, and of course 2 on this particular side, and also right angle obviously there. So this is now my sine of 2 theta, that is where it's going to come from. Okay, so essentially I have 3, 3, and of course a 4. So let's use the cosine rule, because of course if we look at the cosine rule now on this triangle and say 4 squared, I can write this now as, let me actually leave the 2's there and use a different color pen and put this as a 4. So that's now 4 here. Then by the cosine rule, I have 4 squared is equal to 3 squared plus 3 squared minus 2 times 3 times 3 times the cos of 2 theta there. All right, so what does that give me? It will give me, of course, 16 is equal to 9 plus 9 minus 18 lots of the cos of 2 theta. Move the 18 lots of cos 2 theta to the left, so it's going to be 18 cos of 2 theta is equal to 9 plus 9 is 18, take away 16 is equal to 2. The cos of 2 theta is equal to 1/9. So 2 theta, if you look at what happened in there, 2 theta, which is what I'm after, 2 theta is of course 2 times your arcsine of 2/3, is of course the inverse cos, has another C in there, the arc cos of 1/9, and this is done in a very bizarre way. Let me just put there actually what 2 theta stands for, because theta of course is the arc sine of 2/3 is indeed equal to the arc cos of 1/9. Try to give you a little bit of an insight. This is not a particularly difficult question, a little bit unusual. The first time you see obviously inverse trig relationships is quite stressful. I mean, I didn't like them when I first saw them. They're a little bit, they're quite a lot of fun. So I wouldn't say be scared of them. Give them a go. Try to improve on them. They're actually quite good to play with. Okay, I'll see you very soon. Who's laughing now?